So a Russian chemistry professor named Dmitry Mendeleev is often given credit for putting together the periodic table. And this happened back in 1869. He noticed that the elements had some properties in common and they could be grouped. And so he found that if you put the elements in order of increasing mass, the properties recurred in a periodic pattern. So if you list out the first 20 here, these are listed by atomic number, but that mostly corresponds with their mass. So he found that helium and neon and argon had similar chemical properties, and that lithium and sodium and potassium had similar chemical properties. This reminds me of a piano keyboard, where this might be C and this is an octave higher. It's also C and an octave higher, also C. It's the same note, and yet it's not exactly the same note, right? It's a higher harmonic. So there are patterns. So if we put those in a table, which is what Mendeleev did, he put them in a table so that the elements with similar properties were in the same column. So here we have the blue ones stacked on top of each other and the purple. And now hydrogen, we think, well, why isn't he over here? I'll tell you this over and over again. Hydrogen is like the baby brother of the element family. And what happens with that youngest child? Do they have to follow all the rules that the first and second children did? No, they get away with all kinds of stuff. I have a hydrogen in my family. His name is Andrew. And part of the reason, so if you're not a parent, you don't know this. Part of the reason that youngest child gets away with stuff is because the parents are old and tired and they just don't care that much anymore. It's like, it's not worth making him eat his vegetables. They tried harder with the first children. So anyway, so that's why hydrogen just always seems to be breaking the rules. He does that. Sometimes helium does too, but he behaves a little better. So he made up this table. And there were some gaps in the table because not all of the elements had been discovered yet. We now have all the elements through 118. But at that time, there were many that hadn't been discovered yet. Oops. So this is an interesting table. There's nothing we need to remember from this, but I think it's just kind of interesting. This shows time of discovery for the various elements, just in blocks of time. So before 1800, the first half of the 1800s, and here these are discovered since 1950. So this is kind of interesting. So some of the elements, like technetium and rhenium, astatine, these guys had not been discovered when Mendeleev put his table together. And in fact, some of them, like germanium, was discovered in his lifetime, but not at the time that he put the table together. And so he actually he left gaps in the table and predicted that elements would be found to fill in those gaps, and they were. And not only that, he looked at the properties of the elements around them, and he predicted densities and reactivities and all sorts of things, and he was incredibly accurate with that as well. So it's kind of cool. And this is just kind of fun. And this is how, in 1869, Dmitry Mendeleev completed the first periodic table. Right? Chemists have really weird senses of humor. In the modern table, the elements are listed by order of increasing atomic number rather than increasing relative mass. And Mendeleev put a couple of pairs of elements out of order by mass because it didn't work out with the properties. Examples, where'd they go? There's one over here, tellurium and iodine. Iodine weighs a little less than tellurium, and yet it comes after it in the periodic table. And that's because the true ordering principle is number of protons, not the actual mass. There's a lot of information in the periodic table. So this slide shows us some of the major divisions. This dark line here is what I call the stair-step line. I don't know if it has an actual name. It's a very useful line. That divides the metals and the nonmetals. And on this periodic table on the wall, it wasn't originally on that, so somebody got a ladder and put it up there with blue tape because we like the line. It helps us to identify metals and nonmetals. So the nonmetals are up here, and if you have a hard time remembering that, think of an element that you know is a nonmetal. Is oxygen a metal? No, oxygen is a gas that we breathe and helps us to stay alive. So oxygen's a nonmetal. That means this whole corner is nonmetal. Is iron a metal? Sure, iron's a metal. So iron's over here, so then this whole other side must be metals. So that's the dividing line. Along the dividing line are some elements that have intermediate properties, right? It's not a hard and fast, here's a metal, here's a non-metal. There's some kind of wishy-washy ones in the middle. Those are called metalloids or semi-metals. They have properties sort of between. These guys down here are called the lanthanides and the actinides. If we look at this periodic table, and here we have 56, 57, 72, that's not how I count. What happened here? Well, these guys don't fit very well. It makes the table really long, right? And so we have it on the wall here, really long and skinny, right? That doesn't fit on a piece of paper very well, but it does fit on this limited amount of wall space above the chalkboard. So we took that periodic table and cut it and pieced it together like it actually should be displayed. But these are the elements that come after lanthanum, and so they're called the lanthanides. So this, we should take a pair of scissors, cut this, and stick these guys in here, and then the numbers work out better. This is actinium, and so actinium's 89, and thorium comes after that, and so this whole group here is called the actinides. These are rare metals, and we don't run into them very often, and so we put them on the periodic table. They're there, but we kind of stuck them off to the side as a footnote almost. So in words, some of the information here. Metals are good conductors of heat and electricity. Nonmetals are not. Metals are malleable and ductile, meaning you can hammer them into sheets, you can draw them into wires. Metals are not. Nonmetals are not. Metals lose electrons in chemical changes. Nonmetals gain electrons. So you remember the metal properties, and then the nonmetals are the other way. So the most important thing here, metals tend to lose electrons, and nonmetals gain electrons. The metalloids or semi-metals are also called semiconductors, and they have intermediate properties.
So all of the metals are positive ions?
All metals will form positive ions, yes. Now, it is possible to form negative ions from metals, but that's not what they normally do. When an atom gains an electron, is its charge positive or negative? It's negative, right? So the word non-metal starts with N. Non-metals make negative ions. I realized I skipped over something back here. Cations and anions. So cations are positively charged, anions are negatively charged. If you like cats, this works out well because I have positive feelings for cats and cations are positive. If that is not the case for you, anion has an extra N in it, and that's the negative one. That's the best I got for that. More information in the periodic table. So the elements in yellow are called main group elements. And in the blue, these are called transition elements or transition metals. And so you can kind of imagine that this is one bank of a river and this is the other bank of the river. Even they drew it sand colored, how nice of them. And this is the water in between. And so these are the main groups, and this is the transition from one side to the other. We have rows, and we've numbered them 1 through 7, and the rows are called periods. The columns are called groups or families, and those are also numbered. There are 2 sets of group numbers. The International Union of Pure and Applied Chemistry, IUPAC, recommends that we use the ones that just go 1 through 18. Nothing wrong with that, but the current U.S. usage is 1A, 2A, 3A, etc. over to 8A, and the transition elements have ones that start with B. We're currently in the U.S., so that's what I like to use. We actually don't use these group numbers down here at all, but the group numbers for the main group elements are really, really useful and handy. So some of these groups have names, and these are names we need to know. The noble gases, group A, very unreactive elements, and they're gases. The alkali metals are reactive metals. The alkaline earth metals, alkali metals are group 1, alkaline earth metals are group 2. They're fairly reactive, but not quite as much as the alkaline earth. And then the halogens are nonmetals that are very reactive in group 7. So some of the elements form predictable ions. They always form the same kind of ion.
Is there a thing called the halogens? Is that by the halogens?
The halogens?
Yeah.
Yes.
But it's like the name of halogens. It's on the column 6.
You mean with the oxygen?
Yeah.
That group?
I remember like back in chemistry, professor said that by the halogens is collagens.
Chalcogens? I have a vague memory of something like that, but it never shows up in the textbooks, and so I don't remember it.
So we just ignore it.
Yeah, we don't. There probably is a name for oxygen's family, but we don't use it very much. Yeah. So some of the elements form ions where we can predict the charge just by looking at the periodic table. And these are mostly main group elements. So main group elements that form cations with predictable charges, the charge is equal to the group number. Main group nonmetals gain electrons, so they form negative ions, anions. And there's a couple of ways to think about this. They form ions so that they have the same number of electrons as the nearest noble gas. That doesn't help out too much. The charge is the group number minus 8. That can be useful. Or I'll show you when we get to a picture, you can just count backwards from the end of the periodic table. The transition elements are less predictable, and so many of them will form several different ions. Like iron can be +2 or +3, and the periodic table doesn't help us with that. So in general, the group 1 form +1, the group 2 form +2, halogens form -1, and the oxygen family, so he doesn't use the name, tend to form -2 ions. So this is better. I'm a visual person, I like pictures, and if I can't have an actual picture, I make a picture in my head, right? And then I can look at it all I want. So here we have group 1A. All of the elements in group 1A will form +1 ions. Now, is hydrogen a metal? No, he's not a metal. But he's over here on this periodic table, right? Because he acts like it in some ways, in that he makes a +1 ion. So he's sitting over here, but he's not one of the alkali metals. The group 2A form +2 ions. Group 3A, aluminum, 3+. So that's nice. Group 1 is +1, etc. And then here are the nonmetals, and they're going to form negative ions. The noble gases aren't shown here because they don't react. They don't form ions. They just don't, right? They're like the nobles, the nobility in Europe. They just don't interact with the rest of us, right? They're off by themselves. They're too cool for school, right? So those are just going to be zero. They're always going to be atoms. And so what most students like, because I've tried several different explanations, pretend this is like a board game and you're starting over here. This is 0. And if I want to know what the charge on nitrogen is, I'm going to count backwards, because going to the left is backwards, right? -1, -2, -3. So you'll see all of these are -3, all of these are -2, and all of these are -1. And look, there's hydrogen again. How can he be in two places at once? Hydrogen also makes a -1 ion, right? So in some ways, he belongs over here, and in some ways, he belongs over there. So sometimes we put him in both places. There's only one hydrogen. Any questions? Yes?
Question about nitrogen.
Mm-hmm.
On here, I have it in my notes. Is this only forming a -1 charge when it's bound to oxygen specifically? And it's -3 otherwise? Because I remember that this T right here was an exception. I think that was only when it was reacting with oxygen.
Yeah, I'm not sure what that is referring to. That's probably a pattern that I'm not familiar with, but to my knowledge, nitrogen as a monatomic ion is always -3. Now, when it combines with oxygen to make nitrate, then it's -1.
That was my question.
So
Gotcha.
that might be it.
Thank you.
Yeah. So we should be able to predict charges. So we just talked about nitrogen, so let's do something else. Let's do sulfur. Oops. Let's do sulfur instead. What's the charge on a sulfur ion? So here's sulfur. Is it a metal or a nonmetal? It's a nonmetal, so is it going to be negative or positive? Negative. Nonmetal negative, right? So 0, -1, -2. So the question is asking predict the charges. So the charge is 2-. And just for practice, let's write the symbol for the ion. It would be S with a 2- superscript. Okay? Rubidium. Well, first we have to find it on the periodic table. There it is. It's a metal. It's going to form a positive ion. And it's going to be what? It's in group 1. It's +1. So its charge is 1+, and its symbol is Rb+. So from this point on in the class, we're going to have a lot of heads snapping over to look at the periodic table. What's the charge on rubidium? You know, that's where all the answers seem to be. And sometimes when we look at it, even though the answer isn't on there, we think and we figure it out anyway.